All right. So, a big hello to everyone who's just rolling in. This is Computer Science Office Hours with Chegg. My name is Reese, and as people are coming in, just if you've been here before, then welcome back. If you've been to Chegg office hours for other subjects, welcome to computer science. And if this is your first time doing any Chegg virtual office hours, then welcome for your first time. So you can just think of this as virtual office hours. I'm here to help. So if you have questions, just put those in the chat. And um, if you have any questions about any other subjects, you can just scan that QR code in the corner and see the schedule of all our Chegg office hours. But today we're doing binary search trees, pointers, stack frame practice problems, and ARM assembly practice problems. So if anyone has anything else they would want to be covered, just be sure to put that in the chat. I'll be checking in every so often, and if you have any questions, want me to cover things more, just put that in the chat and I'll keep an eye on that and just make sure to switch gears if anyone wants anything else to be covered. And then as you just come in, again, like I am here for computer science. I'm here every Tuesday, 6:15 to 7:15 Pacific time. And if you want any other subjects, just again, scan that QR code. But I think we're gonna get started. All right. So to start us off, I'm going to get into some binary search tree practice problems. All right. So given the numbers 50, 30, 70, 20, 40, 60, and 80, construct a binary search tree and draw the tree structure. So for those of you like just starting computer science or when in it, you guys know that data structures are so important and are such a big thing. But there's like a lot to remember. And sometimes it's just a lot of information. So just breaking things up and remembering the formulas for each data structure is what I like to do. So we have the number 50 first, so that means it'll be our root of our binary search tree. So I'll draw that as the root. 50. And then 30 comes in next. So in case you forgot, with a binary search tree, lower numbers that are smaller than the root, go to the left, so smaller. And numbers that are larger than the root go to the right. So 30 is smaller than 50, so we'll create a new node to the left, and that's 30. And then 70 is bigger than 50, so we'll create a new node to the right, and that's 70. All right, and now we have two branches off of 50. So now we get the number 20, sorry. You've already done these three. So now the number 20 comes in. We check it's smaller than 50, okay, and then we go down to 30, and it's smaller than 30, so 20 goes to the left of 30. And then same thing with 40, it's smaller than 50, but it's bigger than 30, so we'll put 40 right here. And then 60 is bigger than 50 and smaller than 70. So I'll put 60 right there. And then lastly, 80. 80 is bigger than 50 and bigger than 70. So I'll just put 80 right there. All right. So that's how you design a binary search tree for any set of numbers. It's pretty intuitive once you get the formula down of just smaller and larger. And there are a bunch of different like variations of binary search trees. Like there's the red and black tree, which is self-balancing. So if you have any questions about that, just let me know. And for those who are coming in now that we're in it for a few minutes, my name is Reese. I'm here on behalf of Chegg for Intro to Computer Science office hours. If you've been to any of Chegg's office hours, you know that it's like virtual office hours. So if you have any questions about computer science, just drop that in the chat. If you have any questions about like things that I'm not covering, we can switch gears and do something different. And if there's anything that you want me to cover that I don't get to this session, just make sure to check back in next week on Tuesday at 6:15 Pacific time, and I'll be here. And then we can cover new things. And if you have a different subject, make sure to scan that QR code to keep up to date on the different office hours. So a really good question came in from TikTok from All Purple. They asked, why did you start with 50? And that's a really good question. It's only because the number 50 came in first to be stored on the tree. So when a tree is empty, there's nothing in it, right? And we just got the node 50 to be inserted. If a different node was inserted first, then that would be the root. But for a binary search tree, regardless, whatever node is inserted first will be the root of the tree, if that makes sense. And then moving on. Okay. So with binary trees, there are 3 different ways to traverse them. Like, as you probably learned, there's in-order, pre-order, and post-order traversal. So I'm gonna go back up here though to write it. So the in-order traversal of this tree, in order goes like this. This is how I like to remember it. It goes left, and then root, and then right. So for each node, that's what it's gonna be. So we'll start at the root, and then we'll go left, and then we're at this node. So we go left again. Left. And then now we're at this node. We can't go left, so we go to the root. Like left would be null, so we don't do anything. So we just print out the root, which is 20. So 20. And then that checks off the left for 30. And then we print the root for 30. So 30. And then we do right. So we're still on 30, the node 30, and we go right. There's a node here. For 40, we see if there's anything to the left, nothing. Then we print the root, 40, and then there's nothing to the right. So now we're finished with 40. We're finished with 30 because we went to the right. And now we're back up with 50. So we print out 50 because we're at the root. So 50, and then we go to the right. We're at 70. So we do left. If I can select this color, we go left. We're at 60. 60 has no left. So then we do root. So 60. And the colors I'm writing down actually have no significance. I'm just changing colors to give a sense of the fact that we're changing nodes. But I'm just printing them out in order, the in order traversal. So 60, we print out the root. There's nothing to the right of 60. Then we're back at 70. We print the root, 70. And then we go to the right. 80 has no left. We print the root, 80, and there's no right. So another way you can think of root is also like node. So whatever node you're at, you print that node. And then for left, that means you go on the left branch and repeat the process for each node. And you can see how that kind of creates an algorithm where for each node, you do the left branch, and then do the right branch, and then print the node, and then do the right branch. So it's kind of a recursive function that way. And if you were here with me last week, I went over some recursive functions, and I can go over some again, especially in relation to the binary search tree, if you have any questions about that. So in order to cover that again, when I think 20 first, it was 20, 30, 40, 50, 60, 70, and 80. And the reason it's called in order, right, is because it prints out all the numbers in order from smallest to largest. And then we'll do pre-order. Just gonna erase all this. Okay, pre-order is in a different order. So what preorder is it does the node or the root. So it goes root, and then left, and then right. So we start from the root always, like the root of the tree, and we go root, underline that. So we go root, and we print that out, so 50. Then we go left here, and then we hit a new node. So then we start over. So we do root, 30, and then we go left again. So left, and then we've hit a new node again. So we do root, which is 20, and then we go left. There's nothing there, so we know we're finished with that. And then we go right. There's also nothing there for 20. So then we go back up to 30. 30, we go right, and then root, 40, and there's nothing left or right again. Okay, and then we've done the left branch of 50. So now we go back up to 50, and so we did root of 50, that's checked off. We did the left branch of 50, that's checked off, and now we go right. And then we hit 70. So we say root of 70, then left, root of 60, 60, and then there's nothing left or right of 60. And then we're back up to 70, we do right, and then 80's root, and then there's nothing left or right of 80. So our final answer is going to be 50, 30, 20, 40, 70, 60, 80. So that's pre-order. Pre-order 50, 30, 20, 40, 70, 60, and 80. Beautiful. Okay. And then I'm going to go a little bit faster for the last one because I think you guys have understood the pattern now. Oh, sorry. Also, that was pre-order. I didn't rewrite that, but that wasn't in order. That was pre-order. Okay. Get rid of all this. Okay. So the last one's post order. So the post order is going to be left, right, and then middle. So 50 we go left, 30 we go left, nothing left, nothing right, then we print the middle. Back to 30 we go right, nothing left, nothing right, print the middle. Or sorry, I've been saying root. So instead of middle, it would be root. And then we're back to 30, we print the root. And then at 50, we go right, and then we go left, nothing left, nothing right, we print the root. And then right, nothing left, nothing right, we print the root. And then print this root, because we traverse the left and right branches. And then lastly, we print the root of the entire tree, which is 50. So that would be post order. Okay, and then if you guys have questions about that, make sure to ask, but I think I went over those patterns. And if you guys are just rolling in, we're doing computer science office hours with Chegg. My name is Reese, and this is like a virtual office hours type thing. If you comment in the chat, I'll answer your questions about computer science. And if you have questions about any other subject, make sure to scan that QR code. You can see the schedule of subjects throughout the week. But right now I'm going over binary search trees, and then I will do pointer practice problems, stack frame practice problems, and arm assembly practice problems. So if any of those interest you, make sure to stay tuned. Or if you want me to cover something different, make sure to put that on the chat so we can switch gears. Let me finish writing this answer. So this would be 30, 60, 80, 70, and 50. Beautiful. So the different traversals of the tree produce different results because you're traversing it in a different way. All right. So the last thing we're going to do with this tree is we're going to delete the node with the value of 30. So if you were coding this and you needed to delete a node, the first thing you would want to do is find that node, right? And that's a lot easier for us because we can just see that it's right here. But you would need to find the node, probably using some traversal that we just did. And then once you've found the node, copy this. Once you've found the node, then you need to delete the node. Okay. So we've found the node. We know it's right here. And the policy for deleting nodes in binary search trees is if the node has right children, we replace it with the leftmost right child. So in this case, it's 30 or 40, sorry. So 40 would replace 30. So it would look something like this. We have the same tree up until we get to 30. So 50, 70, 60, 80. But then 50's left child becomes 40, and 20's parent becomes 40, and 40's left child becomes 20. So 40 takes the place of 30. And that's our new tree. All right. So that covers binary search trees. If any of you guys want to go more in depth on binary search trees, make sure to pop that in the chat, or if you have any questions about anything I just went over. Next, I'm going to start going over some pointer practice problems in C. If you guys want to go over something different, just again, put it in the chat. And for those of you just joining, my name is Reese. I'm doing Intro to Computer Science office hours with Chegg. And we just covered binary search trees. So if you want to look at what I just did, this will be recorded and posted on YouTube afterwards. And otherwise, then just follow along with these problems. Okay. So we're going to write a program in C that declares an integer x that equals 10, declares a pointer p that holds the address of x, and uses the pointer to change the value of x to 20. So if you guys were here with me last week, we did a couple problems like this. And so if you guys want to look back at that, if you're new, there are some more problems, or if you want to cover something different, I can do that as well. But in C, and I can do a different language if you guys would prefer, but C is mainly the language that deals with the most memory and pointers. So that's why generally when we do pointer practice problems, we do it in C. But C++ also uses pointers in almost the same way. Okay. So I'm gonna write a main function of C. So I have my function main. Okay. So in main, we want to do this first. Okay. So I say int x equals 10, and you guys all probably know how to do that. And then I declare a pointer p to hold the address of x. So I like to draw boxes when I think about memory. So here's my int x, and it has the integer 10, and we'll call it x, and then the address of x is it's almost like where this house is. It's a house address, and then what's inside the house is 10. So it's like if we were mailmen, we need to know where X lives, and that's the address of X. So when I do my pointer P, this is a type of integer pointer, right? And I say that it equals the address of X. So if the address of X was something like OX100, then we would have a variable called P that has the address of X. Put it like this instead. And then P has a different house, so P has a different address, and it would be something totally different. Okay, and then we're gonna use pointer P to change the value of X. So because P holds like the address of X's house, right? If we say like what's inside the address, which is P, we use this little star. If we change what's inside the address to 20, then we say, okay, so P has the value of OX100, so then we find that house, and that's here, right? And then we want to change what's inside that house to be 20. And there we go. So that's how we use pointers. That's how I would like solve this problem of how to use a pointer to change the value of a different variable. And we didn't modify x at all, but x's value still changed. So if we were to print out x now, x would be 20 instead of 10. Okay, moving on. So given this code, what will the output? So again, I really like to draw my boxes because I get really confused going through pointers and like managing everything. So it helps me to have a visual sometimes. But I have this array called ARR, and it's somewhere random in memory. We don't really know where, but it holds 4 integers. So if I draw that, this is its whole block of memory. We call this contiguous memory because it's all connected together in the same place. So if this had the address OX100, this would be 104 OX. This would be OX108, and this would be OXC. And you remember learning this because the size of integers are 4 bytes. So we know that the width of each box is 4 bytes, which is why we increment each address by 4. Okay, so pointer equals array. So that means that we have our own box over here called pointer, and that is going to equal OX100. And we know that because array points to this. Like the array is holding this entire block of memory, so that means the value of array is going to be the starting address of the memory that it holds. Okay, so now if we're printing out the contents of pointer plus 1 and the contents of pointer plus 3, we first have to do pointer plus 1 and pointer plus 3 first. So when it says plus 1, what it's actually doing is in C is it does pointer arithmetic for you. Remember when I said it was 4 bytes the width of this box? Well, when C does plus 1, what it actually does is plus 1 times size of int, and it goes 1 element down the array. So pointer plus 1, if pointer was pointing here, which it is, and we do plus 1, it goes 1 down and points here. So pointer plus 1 is going to be OX104 because it points. Now, to 1 over, which is 20. So it's going to print out 20, and then it's also going to print out pointer plus 3, which is OX10C. So if we go down 1, 2, 3, it points there, which is 40. So the output of the program will be 2040. All right. Okay. This is the last of our pointer problems, and this is just a program to dynamically allocate an array and just showing you how to do that. If you guys have any questions about anything I just went over or are just joining, my name is Reese. I'm doing Intro to Computer Science office hours with Chegg, and right now we're doing some pointer practice problems. So if you have any questions about that, just put those in the chat, or if you have any other questions about computer science in any of your computer science classes, you can put those in the chat, and we can switch gears and just go through those if you want to. But right now I am going to do this program. So we want it to dynamically allocate an array of integers with size n. So we don't know how big n is, and that means it'll be a parameter in our function. So we can our function doesn't return anything, it just prints stuff out. So we'll just call it like make array, or we'll call it print. Okay. So we're getting passed in an integer of n. And the first thing we want to do is dynamically allocate an array of integers with size n. So I don't know if you remember from your classes how to dynamically allocate, but it's this function called malloc. And what malloc does is it's like you're telling the program, you're like, hey, I want this memory and I'm going to give it back to you whenever I feel like it. And that's different from this up here, right? Because you say exactly what you want and the computer does it for you, but sometimes you don't know how much memory you want. Like here we know it's four spaces, 4 integers, but here we don't know. We just know that it's n. So we can't ask for memory at the beginning of the program. We have to do it dynamically on the spot. So what we're going to do is we're going to say that we have an array, and we'll call it array, and we're going to call malloc, and malloc takes the size of how much you want. So we want n integers, right? But we also want it to be integers. So we want it to be n integers, and we want it to be the size of integers, which is 4 bytes. So we do n times size of integer. Okay. And again, like if we did it with this up here, right? We say, okay, we want it to be size 4. So we would say, okay, we want 4 times 4, a 4 times 4 byte of memory, which is 16. And that would give us all 16 of these blocks of memory, because 4 by 4 would be 16, which is why we multiply that. Okay. And then we want to populate the array. So I just do a for loop. So I do int I equals 0, and I is less than n, and then we add 1 to I every time the loop goes back around. And then we want to do the contents of array plus I. We want that to equal I plus 1. And so what that's going to do is it's going to go through the array and give it all the integers with values 1 to n. And this is called pointer indexing, if you remember. Array indexing is like this, array I. They'll do the same thing for the purposes of C. I'm just going to show pointer indexing because it'll help get used to how pointers and arrays work in C. Okay, so I ran out of a little bit of space. I'm just going to make this a little bit smaller. Resize. Beautiful. Okay. And then the last thing is to print the values in reverse order. So I'm going to do another for loop, but instead of starting at 0, I'm going to start at n minus 1. And we're going to do it until we're going to do it while I is greater than or equal to 0, because we still want to print out the 0th indexed array element. And then we'll subtract from I each time. And then we'll do print f %d, which prints out an integer in decimal. And we'll do a new line. And then we want to do the contents of array plus I. Okay, so that'll print them out in reverse order because it starts from the n minus 1 index of the array and goes all the way to the 0 index. And then I have to make this a little bit smaller once again because for the memory we allocated, we have to give it back to the computer, to the heap, as you probably remember. Okay. So the last thing we have to do is we have to free the pointer that we grabbed all the memory that we said, hey, we want this. We have to free it and give it back. So we free array. And then that's it. So that will take in an integer of n. It'll allocate a memory of size n integers, and then it gives the array the integers from 1 to n and prints them out in reverse order and then frees the array. So if you guys have any questions on that, make sure to drop those in the chat. And then next, I'm going to cover some stack frame practice problems. I think a couple of these I covered last week. So if you guys were here last week, just let me know and I can do a different problem. But I just wanted to go over it one more time, just like to solidify that practice. And if you're here for the first time, this is Intro to Computer Science Office Hours with Chegg, and I'm Reese. So if you have any questions about anything else computer science, just also drop that in the chat and we can cover that. And then I'm going to also go over a few digital logic practice problems and some ARM assembly if we get to that. I think last week a couple people asked about some assembly, so I brought that. It's a little bit advanced, but so if you guys aren't ready for any assembly, just make sure to tell me and I won't do that. But if you're interested in learning about that, I can keep going with that. Okay, so I'm going to do the stack frame for the recursive function of factorial. Actually, I'm sorry. Last week I did the Fibonacci sequence, but I did not do factorial. So this will be new content. Okay, so when the stack frame starts out, right, we're gonna have to call it in a main function. Like a program always runs in C starting with a main function. So we'll do int main, and then we'll call, we'll say print f, and we want to print the value of the factorial of 3. And then we'll return 0. Okay, so that's our main function. So the first thing that's going to happen is our main function will get called, and we'll draw main stack frame first. So main will have a return address, and that's where main will return to because it returned 0, so then it tells wherever it returns to that it was successful. So we'll say the return address of main. And then main calls factorial 3. So a new stack frame of factorial 3 is created. Okay, so factorial 3 is called, and factorial 3 has its own return address. And factorial 3 returns right here because it returns and then main prints out the value of whatever it returns. So it needs to know to come back to there. And then what factorial 3 does is it makes a copy of the 3 and assigns it to the value of n. So n equals 3. And then it checks if n equals 0, it returns a 1. So it doesn't. And then it returns n times factorial n minus 1. So it calls factorial n minus 1. So now we call factorial of 2. So same thing. Factorial 2 has a return address. And its return address is right here for factorial 3. And then when factorial 2 is called, it makes a copy of n, so it says n equals 2, and then n does not equal 0, so it returns n times factorial of n minus 1. So that would be factorial of 1. So factorial 1 has its own return address, because when each function returns, then the program has to go somewhere, right? So factorial 1 also goes here, but in reference of the one who called it, which is factorial 2. And then factorial 1 makes its own copy of n, so n equals 1, and then returns n times factorial of n minus 1, once again, which is factorial 0. So hopefully this is our last one. So factorial of 0 starts off by having a return address, and that will also be right here, but in reference to factorial 1. And then it makes its own copy of n, which is n equals 0, and then it hits this. So if n equals 0, it returns 1. So it returns 1. So down here we can track that factorial of 0 equals 1. Okay, so after factorial 1 returns, where does it go? It goes where it's pointing, right there. So now our stack frame is in factorial 1. So our program counter, right, it's at this line, right? And it says, okay, we're going to return n times factorial n minus 1. And it's like, okay, what is n? And it looks at the top of the stack, which is 1. So it says, okay, we're going to return n, which is 1, times factorial of n minus 1, which is factorial 0, which we just did, was also 1. So then factorial 1 returns. We can get rid of factorial 2, or of 0. So factorial 1 returns, and I'm going to pop this off the stack. I'll just get rid of that black box. Okay. So factorial of 1 returned to the same line, right? So the program counter is like, okay, now the next instruction we're going to do is return n times factorial n minus 1. And it says, oh, what is n? And we can see right here that n equals 2. So this time it runs the same instruction, but n has a different value. So it'll say, okay, n is 2, and 2 is multiplied by factorial of n minus 1. N is 2, so factorial 1, which is 1. that equals 2. And then factorial of 2 returns. And where does it return to? It returns to the same line, but the same line, again, now has a different value of n. So it says, okay, we return n times factorial of n minus 1. So that's 3 times factorial of 2, which is 2. So that will equal 6. Okay, so we return 6, and where do we return to? We return to here in main, where we print. And then the next instruction that executes is print out what factorial of 3 returned. So it prints out 6. And that's what our output will be. And then the last thing in the stack frame is outputs 3. Or sorry, output 6. The last thing is that main will return when it says return 0, and it just returns to wherever it was in the program or computer that called it, and it returns with a 0, which we don't really care about because we're just talking about the stack frame for this recursive function. So that was a lot. So if anyone has any questions about that or stack frames overall, just let me know and I can re-explain anything if I went too fast. Otherwise, I'm going to move on to some digital logic and combinational logic. And so if you're interested in that, make sure to drop it in the chat. If you aren't interested in that and want to talk about something else computer science related, ask a question in the chat as well, and we can go over that instead. So far, I've covered binary search trees, pointers, and stack frame practice problems. So if you guys are interested in any of those and want me to do more of those, let me know, or you can go back and rewatch these on YouTube. This will be recorded and uploaded to Chegg's YouTube channel. And if you guys have questions about other subjects, again, like make sure to scan that QR code and then you can see all of Chegg's all of Chegg's office hours. And this computer science one will be every Tuesday at 6:15 p.m. Pacific time. So moving on, if no one else wants to go over anything else, I'm going to draw the truth table for a full adder. Okay. So a full adder, right, it takes in one binary number, or 2 bits, right? For just one, it'll take in bit 1, bit 0, or we'll call it A and B. It'll take in A and B and return C, right? But it also needs to return the carry out, and it needs to factor in the carry in, because if we add up 2 binary numbers, right, like we'll say 1 and 1, then we return 1, right? But we also have a carry out, which is 1. And say that the bits before that we were adding were 1 and 1 also. So we returned 1, and then we had a carry out of 1. We have to factor this into our problem. Oh, I'm sorry, I did that wrong. It was 0 and 1. 0 and 1. But now 1 plus 1 plus 1 is 3, right? So we have an output of 1 and a carry out of 1. All right. So based on that, I'm just going to draw a quick truth table for a full adder. So we have the values of A, B, and the carry in. So those are our inputs. And then our outputs, I'm going to draw in a different color, will be C and C out. So C is what we return as a 1-bit sum, and then the carry out is what carries over to the next bits that we're adding. Okay. So if these were all 0, then then C and the carry out would be 0. If the carry in was 1, then C would be 1 and the carry out would be 0. If B was 1, then it's the same thing. If A was 1 and the rest were 0, same thing. And then if B and Cn were 1, then C would be 0 and the carry out would be 1. I'm gonna make this a little smaller if I want to put this full truth table on this page. Because there are a lot of different combinations of what A, B, and the carry in could be. Okay. So if this was 101, zoom in a little. 101, then it would be 0, 1. If this was, what's next? 110, still 0 and 1. And then if it's 111, then the output will be 11. So there's only two cases, or there's only one case where it would output they both be 0, and only one case where both of the outputs would be 1. Okay. So that's the entire truth table for both. And now we can create Boolean expressions for the sum and carry outputs. So C is the sum, and carry out is the carry out bit. Okay. So we can either write this, right, as sum of products or product of sums. And I'm gonna write the sum of products. So C is gonna be, we're gonna call this D for the purposes of the Boolean expression. Okay. So if A is, this is a not, so if A is 0 and B is 0 and D is 1, then it would be a 1. Or if A is 0, B is 1, or D is 0, then C would be 1. Or if A is 1 and B and D are 0. Or the fourth case is if they're all 1. Okay. So can we see any common factors between any of these? We can see that only one of these can be a 1, or all of them have to be a 1 to be for C to be a 1. And then C out is gonna kind of have a similar expression. So I'm also gonna do a sum of products for that. So if A is a 0 and B and D are 1, then it'll be 1. Or if A is 1, B is 0, and D is 1. Or if A and B are 1 and D is 0. Or if A, B, and D are all 1s. Okay. So those were our Boolean expressions for the sum and carry outputs. And if you guys want me to write it in product of sums, I can do that also. Just let me know. Otherwise, I'm just gonna move on, and then okay. So now I'm gonna show you, like, if you got this problem, like, simplify a Boolean expression using K-maps. So first we have to draw the K-map, right? I always have to move my cursor out of my whiteboard, otherwise it draws that terrible line, but I always forget about it. Okay. So when I draw a K-map, I define that A and A will be down here on the column, and B and C will be on the row. And then I draw all the combinations of numbers that there could be. So A could be 0 or it could be 1. And B could be 0, B and C could be 0, or B and C could be 0, 1, or they could be 1, 1, or 1, 0. And I don't know if you guys remember how to draw K-maps, but the reason I go from 1, 1, 0, 1 to 1, 1 is because when you draw K-maps, only one bit can change per adjacent column or row. So like if I did 1, 0 next to 0, 1, both bits would be changing, and that's not the right way to draw a K-map because then that wouldn't help you simplify it visually. Okay, so now I'm going to fill this in this truth table. So this is a sum of products like I drew before. So this will be, if we draw it like how I did, right? Or write it how I did, 1 is the number 0, 0, 1, and then plus 0, 1, 1, plus 1, 0, 1, plus 1, 1, 1. And that's the same thing as not A, not B, and C. Oh shoot, sorry. I exited out of the tab. You guys can still see it. Or not A, B, and C, or A, not B, and C, or A, B, and C. And then we can fill that in here. So 0, 0, 0 is going to be false. 1 will be true. 3 will be true. This is the number 2 will be false. 4 will be false. 5 will be true. And 7 will be true. And 6 will be false, based on the expression. So with a K-map, I try and make the biggest area I can. So that one right here is easy, right? We can just make a square. And now we can see what is the one bit that stays the same throughout the square, right? So in the square, there we go. A is 0 here, and A is 1 here. So A changes, so that won't help. B is 0 here, and B is 1 here, so that also changes. But throughout this square, C is always 1. So what we can do with that is we can say that the function of A, B, C equals C. So when C is false, the function will be false, and when C is true, the function will be true. So it's like super easy way to simplify Boolean expressions if you learn how to use these kernel maps. And we can test it, right? It's like everywhere where C is 0 will always be a 0, and everywhere where C is 1 will be a 1. Okay. And as we wrap up, if anyone wants me to cover things that I didn't get to today for next week, if you have any questions about anything I've already covered, like as I'm wrapping up, I can go into that. I think I saw a question about big O time, and I can go into that next week and prepare some questions, but it's out of the scope for just today. So if you guys have any other things you want me to cover and prepare for next week, just put those in the chat and I can do that. And then if you guys have other subjects you want to be covered, make sure to scan that QR code and see that live office hour schedule. And if you want 24/7 help, I'm only here for computer science once a week. So if you want 24/7 help, make sure to go to chegg.com. And you can also follow Chegg on Instagram and Twitch and Twitter and no, not Twitter, TikTok, Instagram, Twitch, TikTok, and YouTube. And those 4 places you can get help from Chegg all the time. But for this last question, or maybe we have time for 2 more, but at least this one, This is designing a finite state machine that detects the sequence 101 in an input of bits. So we're just gonna feed a stream of bits into our machine, right? And then as soon as our machine detects a 1, then it outputs a 1. So I'm gonna do a more machine. And in like your computer science classes, if you remember, a more machine means the state outputs a 0 or 1, and in a mealy machine, the transition outputs a 0 and 1. But right now I'm gonna do a more machine. Oh, this is more. Okay, so my state 0 outputs a 0, so Z is always the output. I'm gonna make that bigger. Okay, so Z is always the output. And if it detects a 0, our sequence hasn't started. So we just can keep looping back around as long as it gets a 0. But if it gets a 1, then we need to start detecting the sequence 101. So state 1, it's still going to output a 0 because we still haven't detected the sequence 101. If we get a 0, that's like, okay, we have 2 bits, we have a 1 and a 0. So we'll move on to state 2. But if we get a 1, we're gonna stay at that same state, right? Because we're just gonna be waiting for that 0 to try and detect it. So at state 2, we're still gonna output 0. We still haven't found the sequence 101, but we're 2 bits in. So if we get a 1, then we get it. We got 101 in our sequence of bits, and we're gonna go to state 3 and output a 1. So that's awesome. If we get a 0, then we know we have 1, 0, 0 is represented in the state, and we have to start back over to start detecting a 1 again. So if we get a 1, we'll start back over. And yeah, great question. I can do it in a mealy machine. I'll just finish this one up and then do a mealy machine. More to mealy machine is super easy. Mealy machine just has one less state because it can do it on transitions instead of in states, the return value. Okay. So in S3, we found the sequence 101, right? But if it's a 0, right? What if we're gonna get a 101 again, right? So if it's a 0, we want to go back to this state to see if we can try to detect another 1 and and return another 1 to make sure we're not missing any overlapping 101s. But if we get a 1, then we can start back over and try and detect a 0. So we'll go back to this state if we detect a 1. And that is our more machine. So a mealy machine, I'm just gonna add a new page. And our time's almost up. I have time to draw a mealy machine, but as we wrap up, my name is Reese, and these are the computer science hours, brought to you by Chegg. Thanks everyone for joining. If you have more computer science questions and you want me to go over them next week, make sure to put them in the chat before you go so that I can prepare questions for next week. If you guys want help with your other subjects, again, scan the QR code. And if you guys want help 24/7 when our live office hours aren't running, just go to chegg.com and make sure to follow us on all our social medias. Okay, so a mealy machine, like I said before, outputs a 1 or a 0 on the transition instead. So it's the exact same thing, except we can get rid of these, and we don't need this state, right? So if it's a 0, we output a 0. If it's a 1, still a 0. But here, right, it would output a 1 because when we go back to state 0, we know that we've detected 1 and then a 0 and then a 1, which is our sequence. And then the other transition would be here, which is still a 1. So if we make it to state 2, then we output a 1 either way. We just do it on the transition, which is why we need one less state. But thanks so much for joining, guys. I hope I answered all your questions and about everything computer science related. And have a great rest of your night. Thanks.